Here we are once again, Physics 2A video lecture. Physics 2A video lecture 5. Let me grab a ruler. So we have a couple of announcements. This is the 5th video lecture. The 4th one, everybody noticed, was cut short. Actually, I had an incoming phone call that just stopped the ongoing lecture, and I continued to lecture on. When I finally discovered it, I thought, okay, I'm done for the day, and I just posted what we had. So that was a bit short, and we have a lot of stuff to make up, but otherwise no damage done. So that's the story with the 4th lecture. Next thing, the email notes and homework are working really well. Okay, I've gotten so many great notes, and better than I expected. So people are taking good notes and sending good notes. Let me just reiterate them. So you get these lectures, you want to take as good of a notes as you can. And don't worry about the homework problems until you've taken some good notes, and then we can do some homework problems as well. And some of these you'll find are solved in the course of the lecture. That's fine as well. Just write them down, learn them. They are due, the next set is due Friday, April 3rd. So this is the 5th. There will be 2 more lectures in the course of the week. And some people have sent me more than one set of notes in the course of the week, and I don't mind that either. I just put an extra check by your name. But generally, you're just going to save up everything you have and then lay them all out, get a picture of it to me. Good, so that's that. This, of course, is for both sections, Tuesday, Thursday, and Monday, Wednesday, Friday. So the next topic is the midterm exams. So we're trying to follow our schedule as on the syllabus. So Tuesday, Thursday section, April 16th at 5 p.m. And the idea is we have some time to get this dialed in. I'll send out a mass email at that time with the exam. You guys have your hour and a quarter, and then I'll add some grace period to that as well. But then you take a picture of your exam and send it back to me, and it'll arrive with a timestamp, so that'll all be fine. And the Monday, Wednesday, Friday group the following morning gets another exam, April 17th at 8 a.m. Same thing applies. You write out the exam, take a good picture of it, send it back to me. It arrives with a timestamp. I've discovered that printing out that much paper is hopeless, so I'm just going to have your clearly visible exams, and I'll assign points to them one by one, and when I'm all done, I'll send it back to you with the points, like we did last time, really. And except when I'm done with all of them, I will send the answer keys back as well, and then you'll have the answer key, you'll have how many points you got, and we'll take it from there. That's going to be a dry run for the final exam as well. I have good hopes. I think we'll make this work. The review for this, which will be basically chapter 6, 7, 8, 9, maybe a little more. We're going to start chapter 9 today, or next time. The review for all of this will be when we come back after spring break. We'll be heavily reviewing everything so that you'll go into the exam full of confidence. I made a note about video settings. So these videos are in pretty high definition, and if they're not that clear, you can go to the settings at the bottom of your screen on YouTube and bump up the resolution. You guys probably know how to do that. I'm assuming you do. Okay, so you can get a higher quality if you're not able to read things. Possibly your YouTube settings will allow some improvement. Okay, so much for that. For now, we're just taking the notes, studying, read the chapter, send everything in by Friday, don't procrastinate, get everything done in the last hour. That's human nature. And good, let's get started. I have some demos here, and I had just started spinning the wheel for you the other day, and actually I did a whole lot more. I was there for another half hour, talking away, and then I discovered that my video had been cut short. So we're going to start with angular momentum again. Very rich topic. I brought this angular momentum demo here. This is a gyroscope that I'll get some more controlled phenomena. These things here are when we get into the next chapter and start talking about pressure and atmospheric pressure. We've got suction cups and stuff like that. So I'll put all this stuff to the side. And we'll get started on angular momentum. Okay. Wheel can stay up here for now. So yeah, I was talking about angular momentum. And we've got this wheel, we can spin this wheel. You know, we have torque, twist it one way, twist it the other. It's a heavy wheel, and especially it's filled with something here. But you can imagine a much lighter wheel, say something off of your road bike, okay, which would look the same but would be a lot less massive. Or you can imagine this thing were just a donut of lead, okay, more massive, and one would give a lot of heft to start spinning up, and the other one would spin up much more easily. So you know, we have that rotational inertia, okay, we have the torque, we had Newton's law for rotational motion, and now we're going to get the analogon of the linear momentum, except in the rotational formalism. Okay, so I'll bring this back in a minute. For the moment, we're just going to review the rotational motion formalism. So, review rotational motion. I'll just write rotation versus linear. We got a whole column of things now that are appropriately compared. Okay. So rotation versus linear. Well, the linear, I'm not going to write them all out, but you know the list. X equals x0, t0, t plus a half at squared. Over on the rotation side, we have theta equals theta 0, omega 0 t plus a half alpha t squared. And I'll complete this list. Omega equals omega 0 plus alpha t. The quadratic one we'll leave alone. We have v equals omega r and a equals alpha r if we're going from linear to rotational motion. So this would be translational. Now what else did we have here? Okay, so dot. We had F equals MA, with or without the vectors. Over here we had tau equals I alpha, and this moment of inertia, of course, sum over m sub I r sub I squared. We had kinetic energy equals 1/2 mv squared. Over here we had kinetic energy of rotation equals 1/2 I omega squared. So yeah, we could build all of this up in parallel. What's missing? What's missing here is this linear momentum. I'm just leaving it without the vectors. And what is that going to be here? Well, that's what we're after. What corresponds to the linear momentum? Well, the angular momentum. But we have to get a look at how that comes about. Okay, I'm going to leave these up here for the moment and erase this board and work here. And then we'll really have everything in view, okay. Okay, let's see. So next, we're going to look at torque equals I alpha. Torque equals moment of inertia times angular acceleration. And we can say that is equal to I times delta omega over delta t. Because that's the definition of angular acceleration, change of change of angular velocity over time. Okay, so now I'm going to cross multiply. So tau times delta t is equal to I times delta omega. And now this equal sign here, I'm just going to say this is a generalization. More generally, I'm not doing the fully rigorous proofs, but more generally this could be thought of as the change of the product of I and omega. Okay, and this thing here, where L equals I omega is the angular momentum. So this is the new quantity that was missing there on our chart. L equals I omega, the angular momentum. This one too. Okay, so here's how the argument's going to go. If this torque here, the net torque, if this net torque is equal to 0, then this right side here would be equal to 0, and that means the change of the angular momentum, would be 0, and that would mean that angular momentum is constant, and that's how we characterize what's called a conservation law. This is really the same argument I gave on linear momentum when we were doing collisions. Same argument, except there it was the external force that was 0. Now it's the net external torque is equal to 0. So let's send this up here. And into this box goes L equals I omega. You know, you could have guessed, because the corresponding quantity to mass is moment of inertia, the corresponding quantity to velocity. So yeah, we could have guessed that and filled it in, but here we just derived it, where it comes from. Okay, now I'm going to write down that argument I just stated. I'm going to erase this, write down the argument I just stated about external torque, and then we'll get some demonstrations of this. So now we write if net external torque equals 0. If the net external torque equals 0, then this delta I omega equals 0. That's precisely this whole equation right here. And L equals I omega is conserved. Remember, constant means conserved. Okay, so conservation of angular momentum, L I omega is conserved. And the application we're going to use, so since we have a conservation law, we do these. We say I sub 1 omega sub 1 equals I sub 2 omega sub 2. Because unlike the linear momentum cases we talked about, both of these can change at the same time. So the angular speed and the moment of inertia can change. That's what makes this subject so rich. I don't really have the demos to go with it now that I think about it. I looked backstage and couldn't find them all. However, I'm going to discuss them a lot. Okay, because these are some great examples Okay, so I omega 1 equals I omega 2. The point is this. Here, let's bring out the wheel. Wheel's not really the whole deal. So, the moment the wheel has its moment of inertia, and you know it's spinning now, so it has its omega. And if there's no friction, this will go on forever. But suppose we have some masses inside this wheel that can slide radially. Okay, so if there were a mass inside, right at the hub, if we had some attached masses that could slide, then, and this thing's rotating, and then they slide out while it's rotating, the moment of inertia would increase, and therefore the rotational velocity would decrease. Okay, the famous demo for this, I'm just going to remind you, you've seen it in certain forms. The demo I wanted to show you is I'm sitting on a stool that can rotate, and I hold these masses out, I spin around, and if I pull them in, I spin more rapidly. The reason I say you've seen this before is because you see it in sports all the time. You see it in figure skating, when the figure skaters draw their arms in and they go into a crouch and they spin like crazy. Okay, so they start out spinning slower, they pull their arms in, they spin like mad, or they'll actually have a leg stuck out, and then they'll pull their leg and their arms in. What they're doing is changing their moment of inertia, and if they make the moment of inertia smaller, they make the angular frequency larger. Okay, so it's very common. A diver, someone going off a diving board, they tuck their body into a little ball, they spin faster. It's all over the athletic world. Great examples. You know, if I tried to do the demonstration, I'd probably fall off the stool anyway. Okay, so look around in the sports world. I'm just going to write here demonstrations, see figure skaters, divers, etc. Divers, etc. Okay, so that's the conservation of angular momentum and some of its examples. Let me keep going with this, because the other examples I want go right along with the homework. So the next example, this is actually one of my homework problems I'm going to write down. And that is the central force table. We've seen the central force table, and it looked like this. We had actually, you know what, I'm going to go ahead, since this board is, hey, this board has been fixed. How nice. A day ago the board didn't work, now it's been repaired. That's progress. Okay, set this up anyway. Now we're talking. Okay, so now I'm going to show 2 or 3 homework problems. So these are homework problems. And I'll give you the numbers out of the book in a while. They're written down here somewhere. But the first one is the central force table. We've talked about this central force table before. The idea is you've got a table here. It's frictionless. There's a frictionless mass M here. There's a string, goes through a hole. And before we were hanging another weight on it, and then this thing would go in a circle. So like this, go in a circle of radius r. So that was the central force table. Now in the current problem, we're just going to pull on this with some tension, And here's what's going to happen. If you pull down, the radius gets smaller and the thing speeds up. So if you pull down, we already know there's a tension there against the centripetal force, or providing the centripetal force. Pull down on it, we're pulling against that tension, the thing's going to spin up like crazy. And the question is, how much work are we going to do? If we pull it from here down to here, then the circle's going to get smaller. Okay? The circle's going to get smaller, speed's going to increase. So here's what we have. We have L1 equals L2, so the initial and the final. This is I1 omega 1 equals I2 omega 2. That's how we do conservation laws, right? We just work our way down. Now, however, this next line is really important because the definition of moment of inertia is sum of masses, distances squared. If it's just a single mass, we have mr1 squared. Leave some space here, mr2 squared. And what we have to use is, it's been erased now, we have V equals omega R, so omega equals V over R. Okay, so these omegas can be replaced by V divided by R. So now I have V divided by R, so 1. And I have a V2 divided by R2. Yeah, when the dust settles here, we're looking at mr1 V1 equals mr2 V2. So the moment of inertia times the angular velocity, which gives us the angular momentum, has this form here. So on an exam, if we need the angular momentum in this form, I'll have it on the board. If we need it on this form, I'd give you this on, so you don't have to do the derivation on the spot, but you have to know to look for it. Okay, so this is so important. Suppose we make it from a circle of radius r to half the radius. Okay, if we take half the radius, then we're going to have to double the speed, and that's what this homework problem's about. You're going to find out that the speed has been doubled if you go half the radius, and then you're going to calculate the work. So I'll put this on here so I just keep it on this board. Then, comma, calculate work equals the change of kinetic energy, 1/2 mv2 squared minus 1/2 mv1 squared. So that's what the homework problem is asking you for. Right? It's this, we've been talking about circular motion, tension, and everything, and this brings in a new dimension to it, the angular momentum. And you can build this thing. If you pull on this string, you're going to shorten the length. It's going to spin up faster. One more thing, the reason this is going to happen is because there's no torque. When you're pulling on a string towards the center, there's no torque. Okay, there's no torque on the thing to spin it up, so it keeps the same angular momentum, but the speed does increase because the radius decreases. All right. Good, so that's the one example. The other homework problem has a different scenario. So this is another homework problem. It's also an example. I'll tell you. Example and homework. So on this problem we can imagine we've got, there we go, something spinning on an axle like this. Okay, so there's a disc here spinning like a turntable, omega 1. And we're going to have, and so this one has L equals I1 omega 1. And then up here, we're going to drop a second one on here that is not spinning. So here, omega 2 is equal to 0. And this one drops on here. They stick together and spin together. That's the idea. They stick together, spin together. So what we're going to have is this equation. We're going to have I1 omega 1 before the contact, and then we're going to have I1 plus I2. Okay, so this thing has I1, this thing has I2. We're going to have I1 plus I2 omega prime. That'll be the speed after. Well, what does that look like? That looks exactly like the inelastic collision. And you can say it's the rotational version of the inelastic collision. So it's just a change of numbers, but a change of symbols, but conceptually and formally it works the same way. So you can then solve for omega prime. You can find kinetic energy of rotation before minus kinetic energy of rotation after, and so forth. Just like the linear momentum. So we're using the same formulas basically that we use in linear momentum. We're talking about this thing here. This, by the way, is how a clutch works in a car. Okay, retrieve this thing here. Good, and then there's one more example. I don't know about numbers. This is one that really should bring it home pretty dramatically. Okay. So on this last problem, there are two astronauts. They're separated, by some distance, and they're connected by a rope. So they're both holding a rope. They're out there orbiting the Earth somewhere. They're out there in outer space. Got a rope, but they're also rotating about their center of mass. So here's the picture that goes with that. You've got your two astronauts, and they're holding this rope here. Make this picture big enough. There's the other one. There we go. Hold that rope. Okay, so they're holding this rope, but they're also, there's the center of mass, they're also going in a circle. The circle is something like this. Okay. They're going around in a circle, and they have a speed v. This guy's coming in speed v this way, speed v that way. Okay, how's that for perspective? Could be better, but we get the idea. Yeah, so what's going to happen if they pull towards each other to have a meeting? The closer they get together, there's no external torque. The closer they get together, the faster they're going to spin. Okay. So that's the same problem that I've discussed in a couple with the figure skaters and stuff. As they come closer to each other, they're going to spin. It's a law of nature. They can't slow down. So if they want to get close, if they get too close, they're going to spin too rapidly. It's a conundrum. If they don't have some other means of stopping themselves, it's going to be trouble. Okay, so I think the book tells us there's a separation distance d, and you could say the angular momentum for both of them together is 1/2. It is not 1/2. Sorry, is m times d over 2 times v plus m times d over 2 times v. Okay, so that's just m times d times v. That's their angular momentum. That is what is conserved. If they reduce d now to 1/2, the speed's going to have to double. They reduce d to 1/4, quadruple, reduce d to 1/10, they're going to have 10 times the speed, and things are going to start looking pretty interesting. Yeah, so that's what that problem is about, and once you have this, you can also calculate the initial kinetic energy, the final, the work it takes to do, just like we had with the central force table. Very similar problem. Okay, good. That's as far as we're going to go in this chapter. Formally, I still want to do some demonstrations. Okay. Because the topic of angular momentum is rich, but it's mathematically complicated. And at some point, we can do these basic ones, but there are such interesting phenomena, I want to show you a few of those. So next, angular momentum demos. And I'll write here gyroscopes. Gyroscope, that sounds pretty fancy. Yeah, let's see if we can pull this off. See if we can pull this off. We have the bicycle wheel. Some of you may have discovered this when you were working on your bike sometime. But you probably didn't have a bicycle wheel with a handle, and so this is going to bring the point home. So I spin this thing up, and I can hold it here. As soon as I try to twist it, some weird stuff happens. Okay, I can't just twist it the way I want it to go. It seems to do strange things. Well, apart. Okay, I brought this loop of rope here. What I'm going to do is spin this thing up and then lift it by one side. This is something you have to have seen under the circumstances. Let's see if we can avoid breaking anything. Okay, I'm going to spin this thing up. Spin it up, holding it on this end here. Now, I can't just give a pure lift, but I can do better. I'll lift it out of here. Okay, and then dare me to let go. Yes, about to get injured here. Okay, so I got this unusual effect. It's very controlled. Now, if the wheel weren't spinning, it would immediately fall down as you'd expect it to fall down. As it is, it can keep going for quite a while. I can hold it at a certain tilt. Okay, who's done that before? I remember doing this on my old quick release 10-speed bicycle hub years and years ago. Now I want to continue this demonstration. So I'm going to do the same thing, but then I'm going to choke up on the axle. So I'll start with the loop this far at the end. I'm going to bring it in much closer. See if we can pull this off. Okay. Spin her up. So once again, it's just rotating around like this, okay, with a certain precessional speed. I'm going to choke up on it much closer to the center, and you'll notice it's doing the same thing but at a smaller rate. Okay. This is an example of the vector nature of angular momentum. Okay. The angular momentum vector on this wheel is actually pointing out of the axle. And if I were to choke up even more, this precession will even slow down more. Okay. The gyroscopic effect what we have here, though, if you think of the weight of this wheel acting at the center of the wheel, then there's a lever arm between where the rope is on the handle and the center of the wheel. So there's a torque acting on this thing. Torque is force times lever arm. Okay, we'll put this on the side. The calculations for this are involved, let's put it that way. They're very involved. And on the other hand, engineers, physicists have to learn this stuff. But we want to just see some of these effects. So here's a more controlled gyroscope here, okay? We've got a spinning disc here. And because of these counterweights, it's possible to balance this. Always a little harder than that thing. It's possible to completely balance it so that it just stays there. It's the fine tuning of it. Okay, that's pretty darn balanced. Yeah, I could be at this forever, right? Trying to make it perfectly balanced. Because it has a very good frictionless gimbal right here. Okay. So the perfectly balanced gyroscope, it's as though we were supporting this wheel where we can't, namely in the center of the hub. By the way, this wheel is off screen, isn't it? It's as though we were supporting this wheel right at the center when I support this thing at its balance point. So I'm going to spin it up with this string, not even motorized. We get an interesting phenomenon. Okay. Yeah, we just need to pull on this. Here we go. All right. So the phenomenon that we have is this thing is just pointing in one direction. Its angular momentum is conserved because its external torque is zero. The reason its external torque is zero is because it's balanced here right at the center. Okay? So it's spinning around there. And, you know, ideally, if things were really perfect, I would be able to carry this around the table and it would never change its direction. Well, considering, it's actually pretty good, right? So me carrying this rotating wheel around the table is like the Earth orbiting the sun. So that was just a year. I just did a year's orbit. And where would the Earth be pointing? It would be pointing at the North Star. Okay. But the Earth is not a perfectly balanced gyroscope. The Earth, with respect to the sun, has a little bulge in it. It's rotating. And if I unbalance this gyroscope here, you're going to see something. It starts to precess around the way that wheel did, except in a much more controlled fashion. Our Earth does that as well. And so the North Star it points to, it stops pointing to that North Star, and the astrologers have to find another one. This motion in the Earth is a big spinning gyroscope, okay? This motion that the Earth does takes 26,000 years to complete. There's even the up and down motion called the nutation. So yeah, this is very involved and difficult to calculate, but it's a rich phenomenology. If I really unbalance this thing, it starts doing some pretty wild stuff. Okay. And if I slow it down and unbalance it even more, it just does more of these loopy type of motions. If I rebalance it, so it once again points just wherever I direct it, point it straight at the class. and it's just pointing that way. Okay? So it's a balanced gyroscope. Okay, there are also little toy tops that you can buy that do interesting effects like this as well. So that is something I wanted to show you before we leave this chapter. Very, very rich phenomena with gyroscopes. Okay, how are we doing for time? I think I'll postpone chapter 9 till the next lecture. So what I'll put up now is just a couple of tips. So the homework problems that I just did, let's send this up again. These 3 homework problems were in chapter 8. So you want to make sure you understand them. Homework, chapter 8. Problems, what were they? 71, 73, 73, and 81. Okay, so that's the first thing. And then next, we're going to start in on chapter 9. So go ahead and start reading chapter 9, solids and fluids. Because there's quite a bit of information in chapter 9. Our primary goal is to talk a bit about fluid mechanics, but we need some common concepts. So the first thing we'll be doing in this chapter 9, we'll be talking about density, pressure, and depth. And once we master a bit of this, then just the topic of atmospheric pressure is very surprising. Atmospheric pressure. And yeah, good enough. Then we'll get to Archimedes' principle, but we have to work through a little bit of stuff before we get there. Okay, that'll do it for today. This was video lecture 5. There will be 6 and 7 in the week before we go to spring break. Okay. All right, good. More to come.